So welcome to Interface Fluidics' webinar, where we're talking about how microfluidics can enable progress in carbon capture and storage. Our goal today is to talk about some of the more spoken or represented questions from a technical perspective that we see that the industry is not talking a lot about. So we think there's a bit of a gap in the subsurface question. So I'll be collaborating today with our Executive Vice President of Operations, Ali Abedini, on this presentation. We'll be going through both the beginning of where we came from, as well as Ali will be taking the time to go through the specifics of some of the technical solutions that Interface Fluidics has developed in the past and where we see things going. We're talking about how there's significant investment in carbon capture and storage ramping up. We see headlines just about every day. Most notably, I think Chevron made a big announcement about their $2.5 billion investment in green and blue hydrogen just a few weeks ago. So there's a lot of momentum at play here. And that means there's a lot of questions being answered. Specifically, questions are being answered about the surface. How do we get the CO2? And how do we get the CO2 to the well to sequester it? Less often we hear about what happens when we put that CO2 underground. So talking about filling those gaps, we'll go through three major topics here. The first is an overview of carbon capture and sequestration or storage, just as a very high level intro. Some of the fundamental carbon storage questions that Interface is thinking about, the role that microfluidics can play to answer those questions. And then at the end, we'll just briefly talk about the utilization side, so enhanced oil recovery as well. So the question about where to put CO2 underground is not a new one. People have been thinking about this for a very long time. And there's options that have emerged from depleted oil and gas reservoirs, coal seams that are deep saline aquifers, among many other options. Saline aquifers have emerged as a leading candidate due to the large capacity for the stored CO2 and due to the oil and gas industry's knowledge of how to put fluids into reservoir subsurface. Additionally, the benefit is that saline aquifer is not a useful water source due to the contents of that water. So it's an ideal candidate for sequestering CO2. That being said, understanding how CO2 behaves inside of these reservoirs is paramount to making sure that the capacity that we think is there actually exists and actually gets utilized. So there are two major categories of problem that Interface is looking at and thinking about when it comes to how to put CO2 into aquifers. On the injectivity side, we all know that saline aquifers are highly reactive systems. But the reactions that are in play are significantly different than those seen in oil and gas production. And so this means that they are poorly studied, at least by the oil and gas industry in general. I'm sure there are lots of folks that have done a lot of good work, but in general, the knowledge of this space is lower than for oil and gas production for obvious reasons. This has significant impacts on the storage capacity of these aquifers. On the other side, we're also dealing with phase behavior or fundamental physical properties of these fluids. Pure CO2 is a fluid that is very, very well studied in the literature and not really a problem. But industrial sources of CO2 are not pure, and it's not economic to purify anthropogenic sources of CO2. Therefore, there's an opportunity to understand how these mixtures behave in order to predict how they're going to behave inside the reservoirs. So the physical properties and behavior of CO2 mixtures require further study. As an example of what this looks like, I've just put up a picture here from some work that was done by precursors to Interface Fluidics back at the University of Toronto, where we're studying how CO2 interacts with brine, impacts the solubility of the salts that are present in those systems, and being able to quantify the reactions that are taking place. So with that, I'll pass it over to Ali, who's going to talk a bit about fluid compatibility in saline aquifers.
Thanks, Stuart, and hello, everyone. Again, in the next few slides, I'm going through some of the microfluidics applications to address some of the challenges that we believe we deal with the CCS process. As Stuart mentioned, so one question is around the salt precipitation when we inject CO2 into the saline aquifer. And basically, this is a serious problem for the CCS application, especially when the salt precipitates out of the brine. It can block the pore spaces and reduce the injectivity of the CO2, and it can jeopardize the long-term CO2 storage and security underground. There are some conventional testings out there trying to basically answer these questions. Some of the simulation and modeling have been trying to address this issue. There's some core flooding experiments as well. I mean, all of them, they are helpful to some extent. They can provide valuable information about the salt precipitation, but there is still some gaps here that we believe microfluidics can provide additional insight and data to understand this this process in a better and efficient way. Next slide, Stuart. Yeah. So now we talk about the issue, but basically the answer was given by one of the co-founders of Interface Fluidics, Dr. David Sinton's research lab at the University of Toronto. So basically what we did over there, we designed a microfluidic chip that can represent the pore structure and geometry of typical aquifer formation. And then we look at the pore scale dynamics of the salt precipitation as a result of the CO2 injection into this system. So you can see some of the images. So on the left side, you see the basically different salt precipitation morphologies. You have some crystal-like salt, and also in some cases they actually aggregate together and then produce a larger cluster of the salts that are prone to block the pore spaces effectively compared to these single crystals. And then on the right side, you can see basically the system which is saturated with a brine that can represent the saline aquifer brine properties, and then we inject the CO2 into the porous media. You see the route where the CO2 takes in the porous media, and then the crystallization of the salts and how they basically grow from dynamics perspective. They're either in the single crystal growth, or some of them, they can be mobile and get together and generate a larger salt aggregates.
One of the advantages we see at Interface to this technology is this was demonstrated at standard conditions before the Sinton lab had the ability to go to high pressure, high temperature. So Interface is proposing to move this kind of work over into the world of representative reservoir temperatures and pressures.
That's true. Next slide, Stuart. So again, the other piece is the diffusion. The CO2 diffusion into the saline aquifer is very important for both storage and security perspective. Basically, the CO2 diffusion gives some information about how long it takes CO2 to dissolve into the brine, and also can give us some ideas about the long-term security and storage of the CO2 within the formation. And for that reason, we basically developed a system, again, at the University of Toronto that can measure the CO2 diffusion into the brine. We use a specific pH-dependent fluorescent dye that can show the concentration of the CO2 in the brine. As CO2 diffuses into the brine phase, the pH of the brine changes, and then we see some changes in the light intensity coming from the brine phase. And then by correlating the light intensity to the concentration of the CO2, we can measure the CO2 diffusion in the brine phase. And then on the left side, you see the change in the CO2 concentration versus the distance from the interface of the CO2 and brine, and then some of the diffusion coefficient measurement versus time. And the data that we got from the microfluidics device in terms of the CO2 diffusion, we compared the data against the experimental data coming from some of the conventional lab testing, and including the pressure decay or some of the PVD data, and we found that there's a good agreement between the diffusion data we measure within the microfluidics compared to the conventional data. Again, that's one of the areas that we believe is very important for CCS process, and I think microfluidics can provide a good insight, and also can be a good tool to replace some of the conventional testing that we have to measure the diffusion of the brine into the CO2 into the brine.
Ali, I have a question. I'll jump in here with from the chat. It says interesting work. What ppm are these tests run at? So what concentration are we running these at?
That's a good question. Here, the ppm was 30,000, and it was just basically sodium chloride as a representative. But as Stuart mentioned, again, here at Interface, we have a capability to go to a more extreme condition. And that's a really good point, because the ppm, basically the solid, the amount of the solid or amount of salt in the brine phase can impact the CO2 diffusion as well. So that's one basic parameter that can be analyzed. But this is specific work with a 30,000 ppm.
And then there was another question about pressure and temperature that we can reach. So our capabilities are about 1,000 bar or 15,000 psi and 200 degrees Celsius, 400 degrees Fahrenheit. I'll move on here.
That's good. The next areas of phase behavior. I mean, if everybody basically Google the CO2 phase behavior, we can basically see the phase diagram of the CO2 in 5 seconds. It's pretty simple, but basically we know that when it comes to the actual operations, we don't deal with the ideal cases. There's no pure CO2 that you inject into your ground, either for CCS or CCUS applications. So there's always impurities associated with the CO2 phase. And we believe that that can have a dramatic impact on the performance of the CO2 injection underground. So what we did at Interface, and we developed a state-of-the-art microfluidic chip that can give the phase diagram of the gas that can be pure, not pure CO2, CO2 with different mixtures. And we can have the phase diagram visualized here. So the left graph you see here, basically there's a pressure temperature variation on the chip, and you literally can see the 2-phase diagram of the gas mixture basically in these systems. So literally we have 1,000 different cells. Each of these cells, they have their own pressure and temperature stamp, and they show different basically liquid vapor ratio. And as you can see, you can basically see all the 5 different zones that you clearly see from the phase diagram from the textbook: liquid, gas, bubble point, dew point, and quality lines, which is the two-phase region. So we believe it's a very cool technology to give an idea about how the impurity is going to impact the phase diagram of the CO2, and that can be used as an input data for the models which are supposed to be used to predict the performance of the CO2, either whether it goes into the saline aquifer, or in some cases for the enhanced oil recovery purposes.
Yeah, just to expand on that just a little bit, the business impact here is understanding the sensitivity of any one injection point to the particular impurities that might be there. So you can either optimize this for additional injectivity or mitigate potential risks there.
Sure.
So thinking about this more as a monitoring tool as well as a pre-job planning tool.
The other area is the CO2 films for conformance control. So we all know that there's some issues with the CO2 injection, and one of the biggest challenges is the unfavorable mobility ratio of the supercritical CO2, or just CO2 as we inject into the ground. So foam agents are designed to somehow alleviate that problem by increasing the CO2, the viscosity of the CO2 phase, and consequently reducing the mobility ratio, so we can have a more consistent flow of the CO2 into the reservoir. So there are again some conventional lab testing out that can be used to look at the performance of different foaming agents. Here at Interface, and with partnership with Aramco Services, back 3 years ago, we designed a microfluidic device that can we use to test different foaming agents at different operational parameters. We can test the foam quality, we can test different concentration of the foaming agent, and also we can do all of these on the measurements with different brine salinity, which is going to have a dramatic impact on the performance of the foam and its stability. Overall, we measure some critical parameters. One parameter is MRF, mobility reduction factor, which corresponds to the improvement of the mobility of the CO2. So the higher MRF, the better mobility of the CO2 phase, and we can test it again against different variables. The other piece is this looking at the stability of the foam. Ideally in conventional testing, people use the column testing or tube testing to measure or to quantify the stability of the foam. Here, which basically that method is good, but it lacks the porous media. So it doesn't cover the confinement, which we deal with in the porous media. But here we measure the foam stability in the porous media, and we can see whether these foams can perform long-term or short-term, and what would the implication if we go into the actual operations. I guess we got a question on this slide, Stuart. Maybe if you don't forget that.
Yeah, absolutely. So what is the time frame of these tests? How long did it take us to run these foam experiments?
I mean, typically it's 1 day. To get the MRF, it's a few hours, but to foam stability, it really depends on the quality of the foam and the performance of the foam. So for foam stability, I guess, as you guys know, we measure the half-life. So depending how long it takes to reach the half-life, but typically it will be done in a day or two.
And then if we go back to the salt precipitation studies in porous media, how long do you expect those to take?
Again, they're all in the same frame. Again, it really depends on the kinetics of the salt and the CO2. Again, it's a variable that need to be tested, but those are specific tests that we showed. It was from the University of Toronto. It took over a day.
Yeah, so the question here of how quickly do we see salt plugging of the pore space? The question, I guess, is we see salt precipitation very quickly on an order of minutes. The question of when did the injectivity issues come in? That's really what we're looking at. There's one more question here around the chemistry being approved in the US at state level for subsurface injection. All of the chemistry we've worked with so far is, we believe they are all approved. So if you're curious to know more, I think the actual products that were used in this study with Aramco are named and can be accessed there.
The data in this work is published in the Scientific Reports Journal, so you guys are more welcome to take a look. One more note, which is very noteworthy to mention here, is basically this is the tool that can give an optical access to the porous scale phenomena. And one thing which is very important here is, I mean, when we run all of these foaming agents at high temperature, extremely high temperature, let's say 150 degrees Celsius, there could be some sort of degradation to the chemistry of these agents. So basically, when we measure the MRF, mobility reduction factor, the extra pressure drop that we get, it could be due to the basically deposition of these foaming agents rather than just basically the foam quality. So one of the good advantages of this tool is you can actually look at whether that MRF is due to the foam or just because of the degrading of the foam agents within the porous media. So we saw some examples that basically at temperatures above 200 degrees C, we saw actually the foam chemistry degraded in the porous media and precipitate some sort of the solid in the system.
Yeah. Another question here that's always comes up is how important or unimportant is the geochemical interaction that are not actually in these chips?
Short answer, they're important. But here in our system, our focus is more on the fluid-fluid interactions, which we believe is one piece of the puzzle here. When it comes to the rock and geochemical interaction, so basically we use a silicon substrate here, so they can represent the sandstone pretty well. We also treat the surface chemistry or weathability of these chips. using some proprietary, protocol that we have in the lab. We can change the surface properties to be either water wet, oil wet, or even mixed wet within plus minus 10 degrees of contact angle, which we have a tight control over that. So we don't capture the actual geology on these chips, but we try to basically make the system as close to the actual case to run the fluid-fluid interactions here.
Well, this is one of the more common questions we get, and the way that we approach understanding this is, I said at the beginning that these are highly reactive systems. We know that the rocks are highly reactive as well as the fluids. The goal with microfluidics is to be able to disaggregate the rock fluid reactions from the fluid-fluid interactions. There are, this is not a one-stop shop to get a silver bullet of data. This is another tool in the arsenal for people that are developing these kinds of questions, and being able to understand whether or not the challenges they're seeing are fluid problems or fluid rock problems. That's the key advantage here, is the control over that system. I see we've got a few more questions coming in here, but we've just got a couple more slides. We'll get through that and we'll come back to the rest of the questions that have come in. So last thing here, Ali will talk about some of the CO2 EOR work that we do.
Yeah, exactly. Again, whenever we talk about the CCS, I guess it's supposed to talk about the CCUS as well, or the CO2 EOR, because at least at this point, it's the most practical and feasible approach to store CO2 underground. So basically, whenever we talk about the CO2 EOR and the gas injection, the first parameter comes into the mind is the MMP, because any successful implementation of these injection schemes critically relies on the successful measurement or accurate measurement of the MMP. So the gold standard method out for MMP measurement is steam tube, as everybody knows, but it's a bit challenging to work with the steam tube. It requires a lot of volume, live oil. It's very time consuming. Sometimes it's very operator dependent, and it's very expensive. So here at Interface, and in partnership with Equinor, we designed a microfluidic system that can measure the MMP much faster, easier, and cheaper. So we can literally measure the MMP in few days. And we tested a lot of oil and gas pairs. Some of the data have been published with Equinor at the JPSC. So we tested different gases, including CO2, with different oils that basically produce different types of miscibility mechanisms, CV dry, vaporizing dry. And when you look at the MMP coming from the microfluidics and compare it against the steam tube MMP values, there's a very tight agreement between data. So again, and this is something that have been using the market for the past few years. So we've done a lot of these testing with a lot of operators. And yeah, that's on that. Next,
one of the newer applications we've been working on here is understanding how different kinds of business decisions can be made with this information, because just developing a new measurement is not necessarily advantageous, but what's the new application that can be used? Ali, maybe you can tell a bit about that project we're working on.
Yeah, exactly. So right now we are working with a CCS operator basically in Alberta. And we are working with them to monitor and optimize their CO2 injection. The reservoir pressure is low, and there's not enough cushion, and basically to lose the MMP going above the reservoir pressure. So, and the CO2 stream going into the reservoir is not pure CO2. It's got its own impurities from the pipeline, as well as there's a mixture of the CO2 with the produced gas going to the reservoir. So there would be some sort of the impacts on the MMP. So through that work, we have a detailed test matrix to look at the impact of the different impurities, such as H2S, hydrogen, argon, different hydrocarbon gas mixtures on the MMP. And then trying to make sure that basically we work within the guideline and workflow that makes sure that we are not falling in the immiscible basic injection, which everybody knows that it's not favorable from the EOR purposes.
Yeah, and so the goal of having our technology be deployed to the field or to nearby laboratories is We want people to think about this similar to how they think about a rapid COVID test, which is, point of care understanding of data collection. We want to move fluid analysis from a one and done to an ongoing monitoring with the ability to react in near real time, whether that's for carbon sequestration or for enhanced oil recovery. The same philosophy applies. So just to sum up here, what we talked about today is some of the applications around gas-brine compatibility studies, the behavior and deposition kinetics that need to be studied inside of porous media, as well as the applicability of CO2 foams or basically any other conformance control chemistry that can be used. Additionally, we talked about how CO2 diffusion is going to be sort of the long-term thermodynamic effect that drives the capacity of these aquifers, and so therefore needs to be understood well, as well as the minimum miscibility pressure of CO2 and various fluids in order to understand the application for CO2 enhanced oil recovery. Our goal is to get you better data faster and help everyone lower their emissions. So with that, I'll turn it over to the audience here for any additional questions. I'm just looking at the chat here to see what else has come in since we've been chatting. There's a question here from Enoch. Were we able to run our work with projects within CO2 mineralization or reactive flow systems?
Again, if we talk about the mineralization in terms of salt precipitation, yes. But if we talk about the mineralization in terms of the CO2 reaction or CO2 brine reaction with the in situ formation, at this point we haven't developed that, but there's some proof of concept that we look at the mineralization or dissolution of the minerals in the porous media, especially when it comes to the carbonate system, as the CO2 brine solution interacts with the mineral within the rock. So yeah, I mean, great. That's how basically we address mineralization.
I think one other question that did come up before here is through email is we're very focused on the subsurface, and the reason we're so focused on the subsurface is one, that's where the majority of our expertise lies, but that doesn't mean we often work with sort of collection and midstream systems. But the real thing we see here is a lack of understanding of how the porous media behaves and how these fluids behave in porous media. You can look at lots and lots of studies, and there's billions of dollars being invested into surface infrastructure with the assumption that the tools we use to predict behavior in subsurface for oil and gas will behave the same way for CO2 and be as effective. And what we've seen and heard from the industry is that's not the case. We need additional data to tune these systems up for predicting how carbon capture and storage works when there's no oil in place. So with that, I'll say thank you very much to everybody that's in the audience today. Thank you for all the great questions, and we look forward to connecting with you afterwards.